Good day, everyone. Today, me and my peer Yiwei will talk about what we have done throughout our assignments for FIT3183. So here's a quick introduction to our team. We chose the dark side, and our team name is Watermark Removers. So here's a summary of our topic. And we also provided the reference GitHub, the reference paper, as well as our Google Colab link. So what is watermarking? Watermarking appears in many aspects, such as images, where changes in pixels value or colors, audios, subtle change in frequency, as well as videos, where frame-based changes or encoding tweaks. So how watermarking works? It is a technique that embeds recognizable signals into AI-generated contents that makes the content traceable and protected without compromising its quality. In terms of visibility, there are invisible watermarks as well as visible watermarks. For invisible watermarks, the watermarks embedded are not directly noticeable using human eyes and can only be identified using a detection system. As for visible watermarks, they are obvious and easily recognizable, such as a logo on an image or a text overlay in an image or a video. So there are two examples of watermarks, which is robust watermarks and fragile watermarks. For robust watermarks, they withstand the content alterations such as compressions, cropping, scaling, as well as editing. For fragile watermarks, they are easily destroyed by modifications but are still useful for verifying the integrity of the original content. There are a total of 2 stages of watermarking. The first stage is embedding, which is also known as encoding. The second is detection. So for the embedding process, it can be achieved in many ways, such as adding noisy patterns or modifying low-order bits. As for the detection process, it can be done using algorithms, such as looking for specific patterns or statistical anomalies in contents, or even training a model to distinguish watermark content. So what we have done, what improvement that we have done? We added the regeneration attack, which is an attack method to manipulate the latent space of an image to reduce or remove watermarks. So what are the stages of the regeneration attack? From an original image, original watermarked image is then encoded into the model's latent space, where the Gaussian noise is then added, disturbing latent representation. Next, the noisy latents will then be decoded back into image, resulting in an image with removed watermark. In short, this method alters the image by modifying its latent encoding, attempting to remove the watermark from the AI-generated contents. Here is an image where it shows the process. So from an original image, it adds watermark, which will then cause a watermarked image. It is then embedded into a latent representation where it adds noise and regenerate the image, where it will return a result where a watermark is not detected. I will now pass over to Yiwei to explain more.
Alright, so before I introduce another attack, which is DCT-SVD perturb attack, let me first introduce what is the DWT-DCT-SVD watermark, which we basically use in our code. So first of all, DWT, which stands for Discrete Wavelet Transform, we actually break the image into 4 main parts, which is LL, HHL, and HH. So usually we will choose the LL region to hide the watermarks because the LL region, which will actually usually store the key feature of the image, and during any kind of compression or any image transformation, the LL part is not likely to be destroyed since it stores the key features of the image. Then we will perform the DCT, which stands for Discrete Cosine Transform, which will transform the previous LL part which you choose into frequency coefficient. So the watermark will be hide in the mid-frequency area. So why don't we hide the watermark in the high frequency or low frequency? So high frequency is like the details of the image. For example, if we hide the watermark inside the details of the image, it might change how the image actually looks. And for the low frequency, it is actually the plain color or the blank part of the image. for example, a sky of human face. So if we hide watermark inside the low frequency, you actually, for example, just like painting on a sky, which make the watermark it's not invisible but very visible. So we choose the mid frequency to hide the watermark. And then followed by the SVD, which will later turn the frequency coefficient into three main part. For example, UV and sigma. So sigma is the singular value vector part, which actually store the key feature of the frequency, and U and V will store some other small details. Then the watermark will be hidden inside the sigma part, as it is not easy to be destroyed. So now we will introduce our DCT-SVD perturb attack, which is a specific attack to attack the watermarking method used previously. So since the watermark is stored inside a singular vector, which is a sigma part, this attack will basically modify the first few values of the singular vector to try to destroy the watermark. And then next, we introduce another attack, which is multi-stage attack. So this attack is basically a combination of few attacks together. So the first attack will actually store the result into a temporary file and then pass it to another attack recursively. So the multi-stage attack is our another approach to achieve a higher attack success rate. And next, I'll move on to the Colab demonstration. So this is the Google Colab which our code in, and the watermark we actually embed is the word called TEST. And then here are some few watermarks we use, which is DWT-DCT, DWT-DCT-SVD, and Rebagan. Rebagan is a watermark method which actually use AI to encode the watermark. And then what we done is we actually increase the sample size. Instead of original 6 image, we actually increase the sample size using the COCO dataset URL. And based on the variable here, we put 50, so we add in another of 50 images. So we can also increase the watermarks for the sample size further. For example, we can go for 500 or 5,000. But what will happen is the runtime will significantly increase a lot. So in here, the content we use 50 image. And then here are some attackers we used to attack the watermark previously used. So it is a mixture of the map-based attack and the AI-based attack. And let's move to the next part. So this is the part we actually added watermark to our pictures. And this is the part we actually done our attacks. So let's move on to the visualization of the result. So from this diagram, you can see that the original image and the watermark image, for example, in this case, DWT-DCT watermark. So even though without any attack, watermark actually will decrease the image quality of the original image by 3 aspects, which is PSNR, SSIN, and MSSSIN. So even though without any attacks, the adding of the watermark will actually decrease the image quality of a picture. So let's move to our next visualization, which is the watermark image bit accuracy. So the watermark image, we actually try to decode it back. So we actually encode the watermark and decode it back. See if the decode actually will success 100% or not. So for some example, it actually success for all the bits, 32/32 bits. However, for some image, for example, in this case, DWT-DCT, in this case, it only success around of 30 out of 32 bits correct, which the last 2 bits is actually incorrect. So even though without any attacks performed yet, the decode will sometimes make some error when it decodes back to the original content. So let's move next to the actual attack parts. So as we can see from this diagram, the attack part actually decreased the bit accuracy a lot, from the 90% or 100% all the way down to 46.88%. So we can see that after the attack, the bits accuracy only left with 15 out of 32 bits are correct. So how do we actually determine that if the watermark is successfully destroyed or not? We actually determines based on the bit accuracy, which 24 out of 32 is above 24 out of 32 is considered success, which is a rate of 75%. So the bit accuracy below 75% is considered as fail to detect the watermark. So here are some bit demonstration of our attacks. So let's now move to the next part of visualization. So based on the previous attack method, we can actually group them into a math-based attack and also an AI-based attack. So as the diagram shows, after the attack, the bit accuracy of math-based actually higher than the bit accuracy of AI-based attack. So this result shows that the AI-based attack is actually more success as the bit accuracy even lower. So for the watermark survival, we can see that if the bit accuracy is lower than 75%, we consider it as we cannot detect the watermark anymore. So for the AI-based attack, surprisingly, we can see that there's 0% of success rate, means that all the image after the AI-based attack is the bit accuracy is actually below 75%. However, for the math-based attack, they actually have a 0.24%, which is 24% of the survive rate. So we can see from this result also, the AI-based attack is actually a more powerful attack compared to the math-based attack. So it is worth to use AI-based attack over the math-based attack. Actually we have a few more attack methods inside the watermark.py file. As for your own research interest, you can try on it. So I think this is all for our code demonstration part. So now I'll pass my mic to Nigel to explain about our targeting lab team.
Thank you, Iwe, and I'll now move on to a brief explanation of our attack to our target team. So due to the time constraint, we were not able to perform a hands-on attack to our target team, which is the light Mangouard team, due to actually around the end of assignment 1, I've requested the team for their collab, but they have yet to reply, and we were not noticed about the public of their collab. Therefore, we had not had the time to have the attack. So here is one of the overview of the attack that we have researched on that could possibly bypass their detection system. So in order to target their system, we can create higher resolution deepfake video images, such as it can reduce the visible artifacts by left by lower quality face generation processes. Using it, the warping artifacts are less noticeable or maybe even undetectable. So what we target? We can create high resolution deepfakes where face area has lesser inconsistencies with surrounding context. This will allow it to be harder for the detection system to detect subtle artifacts that could be present in lower resolution videos or images. So how this works is higher resolution images can be achieved by using advanced models which are capable of generating high quality images. In addition, super resolution techniques can be used to upscale deepfake generated images, which tends to have a lower resolution to ensure the realism of images while reducing artifacts. This is also proven by research that we have done here. Now I'll pass it back to Yue to explain more technical details regarding the attack.
Alright, so this is another approach of our attack. And below is our attacking phase. So first of all, due to the time constraint, so we actually use our collab to perform the attacks. So we attack through adding watermarks to the deepfake image and then using our watermark remover to try to remove the watermarks as well as the deepfake image AI artifacts. So the attack use are listed below, which are Diff Attacker and Chang 2020 MSSJ 2018, which is both is VAE Attacker and JPEG Attacker, DCT-SVD Attacker, Multi-Attacker, and Regeneration Attacker. So the first diagram shows that we have added the watermark to the deepfake image. So actually degrades the image quality for a bit. And the second diagram shows that after the decoding, we can only decode some of the correct bits only, and hopefully that this approach could somehow destroy the deepfake AI artifacts. And this is our attacking results. So we can see that actually from the result we can see that the bit accuracy actually drops a lot because the watermark we embedded inside is destroyed, and we hopefully by this approach we can also destroy the deepfake artifacts as well. So next, so as these all are the results of our attacks. So unfortunately, due to the time constraint, we actually the attack we actually performed did not actually pass their group's collect deepfake detection, which is from face swap image PNG2 to PNG8 is our result correspond to the attack method we used before. So from this picture or result, we can see that the picture is still detected like highly unlikely to be real. And next. And we also have a image that detected almost no chance of being real. And yeah, unfortunately, all of our attacks actually fails to bypass their deepfake image detection. Okay, then I think that's all for our demonstration. Thank you.